Hello and welcome to our webinar, Framework Driving Systems Engineering Practices. My name is Michael Gans, Senior Program Manager for Life Sciences at Dassault Systèmes, and I will be moderating this session. This is the second webinar in our 5-part series, Model-Based Systems Engineering for Life Sciences Applications, in which we cover numerous topics we hope will help you advance your MBSE practices. And now I'd like to introduce today's presenter, Ron Kratzky. Ron is a senior solutions consultant for Dassault Systèmes, CATIA No Magic. He has over 30 years of experience in complex systems management and systems engineering. He spent the first 20 years of his professional career as a U.S. Navy surface warfare officer, specializing in the operation, maintenance, and management of Navy nuclear power plants and shipboard combat systems. Ron is formally educated in systems engineering, having completed a master's degree in systems engineering during his final assignment on the Navy staff in the Pentagon, where he participated in integrated mission area analysis and developing capability requirements for the Navy in coordination with the Department of Defense Joint Staff. Following his Navy career, Ron provided systems engineering, design support on advanced systems for a number of government organizations, including the Department of Defense, Department of Homeland Security, Defense Advanced Research Projects Agency, Defense Threat Reduction Agency, and the Joint Program Executive Office for Chemical and Biological Defense. Over this time frame, he has had the responsibility as a Chief Systems Engineer, Chief Systems Architect, and Project Manager. He has used model-based systems engineering methodologies and tool sets for more than 15 years before joining the CATIA No Magic's team as a senior solutions consultant. Ron has written papers, provided presentations, and participated as a panel member on a number of system engineering topics at the International Council on Systems Engineering meetings, IEEE Systems Engineering Conferences, and National Defense Industrial Association System Engineering Conferences. Ron is a certified systems engineering professional through INCOS, a certified Six Sigma Green Belt through American Society for Quality, a SAFE practitioner, and a certified OCSMP model user. And now, if you're excited as I am to hear Ron speak, let's turn it over to him to begin today's presentation. Ron, it's all yours. Thanks so much.
Thank you for that introduction. Today we're going to talk about systems engineering practices, and we're going to look at how the systems modeling language is used to in systems engineering and model-based systems engineering. And we're going to walk through also a framework that we've developed here at No Magic to help to assist us in using the systems modeling language to do system design. So overall, we're going to look at the CATIA portfolio and how the Cameo Systems Modeler toolset fits into the CATIA family and the overall system engineering lifecycle. We're going to talk a little more about systems modeling language, and then we're going to talk about how MagicGrid addresses the transition from getting initial requirements, which are generally stakeholders' needs or marketing needs or things like that, and how we can transition from that into an operational concept and then develop what we call the logical and physical architecture of a system. So first, let's talk through how CATIA Magic, the Cameo Systems Modeler, fits into the overall system engineering lifecycle. This diagram is a little busy here, and it is based on a diagram that, or a concept that NavAir has put together in the military to talk about how they're going to do model-based systems engineering. But the diagram is very useful for us in this context of life sciences in that it shows us the basic things we're trying to do when we do a system design. Generally, we have a number of external requirements that are shown that we have up here, and we have to take some external requirements, whether they're some mission-based needs or some capability requirements, or even some very high-level stakeholders that say, here, I need to do this with our system, or we need to change the system somehow. And we get into this thing called the systems model. Now, many times that systems model consists of a bunch of requirements and maybe some other diagrams. What we're trying to do in the MBSE environment is to put all these diagrams together and all of the text from the requirements together and show how we can produce a model-based system so that we can provide traceability between things like the structure of the system, the behavior of the system, the requirements that we have written, and those are all textual requirements, sometimes in spreadsheets, sometimes in Word documents, and then do some analysis of the system in terms of parametric diagram. And eventually this systems model, which shows this linkability between all of these, gets developed to a certain point where then we end up doing some mechanical design, electrical design, software design, and other testing methods and models. Now, these things down here in this detailed design phase is something we're going to talk about in subsequent lectures or subsequent webinars, where we're going to talk about how do I do a 2D model for the mechanical design or the electrical design? How do I then also do some modeling and simulation, very unique, specific modeling and simulation? In the systems modeling, you're going to see a little bit of this. I can do some modeling and simulation. I can do some trade-off analysis here in the systems model, but eventually I get to a point where I have to get into that detailed model, and that's what's done down here in this detailed design. So we have this notion here of this descriptive model, and you'll hear me say that the descriptive model is what the model-based systems engineering provides us. And then we have an analytical model, which is down here in the system design, in these individual design models. And so we're going to focus today on how do I take some external requirements, how do I then bring them into this model-based system engineering environment, how do I conduct some analysis, do some traceability, and do ever increasing details on my design and get it to a point where now I have described my design such that I can then go into this detailed design work that's needed in the rest of the platform, or that's actually accomplished in the rest of the platform. So to get into this, we have to talk a little bit about what systems architecture is and what it means and what is a system design. And so the things we talk about here at Dassault Systems come from the International Council of Systems Engineers Handbook. That's in COSI's handbook. And we talk about system architecture, we talk about the creation of a high level or abstract understanding of what it is we need to design. And eventually that systems architecture then becomes a system design. And that gets oriented through the logical, physical, structural elements, the details of what I need in my system to meet that high level system architecture or concept of operation. Well, if we look at this and take this to another step deeper, we can kind of break this out into a different understanding here, graphical understanding. ISO 15288 is an international standard for systems engineering and systems and software engineering. ISO 15288 is the basis of the COSI handbook. So the two documents, ISO 15288 and COSI handbook, work hand in glove together. So if I'm over here on the left-hand side of this diagram, and I have business or mission things that I need to do, I then need to turn that over to the systems engineers to look at it. And so I've broken up the ability to do the design into some problem area, into a problem area, then a solution area, and then finally an implementation. And the systems engineering team works in the very top level of this diagram. We take the systems engineering needs and definitions, we come up with an operational concept, how to transform those stakeholder needs into stakeholder requirements. And then how do I get that architecture definition, that high level design definition, and work my way down into this detailed design where I actually describe in here the actual configuration items and the parts of the system that I need to design. And along the way here, I've shown this, and I should say before I go further, that there's specialty engineering that's used throughout this whole process. Safety engineering, security, human factors, those sorts of things are used across this entire life cycle of doing this design. So this model-based system engineering world, this descriptive design, is going to handle this very top level, taking the operational concept and driving it down to get some detailed design definition. And then the platform that Dassault Systems has will take this architecture design that we put together, and we can then marry that up and link that to the 2D, 3D models through Simulia, through all those different things that we need to do individual industry area designs. And this is the detailed design level that's in the platform. So let's go back up and talk about how we're going to do this high level design. Again, just another way to look at this is showing that this is the model-based systems engineering part of it. This is I call it model-based design down here, which is using these individual models, these high level, high detailed, high fidelity models as the underpinning or the foundation to the model-based systems engineering. To take this another step further, what we're doing here in this high level systems architecture is going from a conceptual understanding to a logical and then into a physical understanding of the design. So we're talking about how do we take business needs, stakeholders' needs, requirements, and develop an architecture, get a high level design. Along the way, we may create some conceptual 3D models or 2D models and do some high level analysis, but eventually we get to this detailed design where we move from the model-based system engineering world into the platform and then do this detailed design for the system. Along the way, just to give you a glimpse of this, the idea behind the digital engineering is taking this model-based system engineering world, taking this detailed design world, and keeping those up, keeping those models relevant all the way through integration, tests, and operation and sustainment. So if we're going to do this design, how are we going to do it? We use something called the systems modeling language to great effect as we do this. So we're going to talk a little bit here now about why use the systems modeling language. Well, if we try to create something, if everybody speaks one language and we're all talking the same thing, when I say a requirement, we all have an understanding of what a requirement is. We all have an understanding of what a structural diagram is. If we have one language that we use to do this, then that will enhance our communication and enables us to understand one another very unambiguously. So the systems modeling language, which is developed by OMG, is a standard that many teams are adapting across many industries, from military, aerospace, oil and gas, automobile manufacturing, and it's even finding inroads in very unique things like Amazon is starting to use systems modeling language to help define and describe how they want to do package distribution. So by using this language, we all have an understanding of what we mean by a requirement, what we mean by a structure, what we mean by an internal block diagram, what we mean by connectors and interfaces and things like that. So we adopt that language to do that, to do our design. The systems modeling language is a graphical modeling language in that I can express things about the design in a graphical way. And when I express things in a graphical way, that the fact that I'm putting things on a diagram has underlying meaning. And those lines and edges and nodes we put on a diagram provides us relationships between certain things. So for example, when I have a block and I draw an association from one block to another, that makes a relationship between that, shows me that this one block is decomposed, or this one entity in the system gets decomposed by lower level entities. If I have a requirement and I draw a relationship from one requirement to another requirement, and I can define that relationship, is a lower level requirement a refinement of an upper level requirement? Am I tracing to other things in the architecture? I can show relationships from requirements to other objects in the architecture. That's with a satisfy relationship. So there's this understanding of not only having the objects on a diagram, but an object that has an edge that connects it with another object on the diagram that shows me a relationship. And so over the years, we have a number of modeling tools that have supported this. And now in the Dassault Systems line, we have the No Magic product called CATIA No Systems Modeler, which allows us to design the systems using the systems modeling language. So the systems modeling language has 9 diagrams, 4 different categories or pillars. And this graphic here shows me the basic structure, the basic categories. We have structural diagrams, behavior diagrams, requirement diagrams, and parametric diagrams. And all these diagrams look different. This particular diagram is what's called an IBD. This particular diagram is what's called a state machine diagram. So this diagram is actually a table, and it's a table in German, but what I'm trying to show here is that the tables are considered to be diagrams. So this is just another way to express the information in the model is through tables. And this is a parametric diagram. This allows me to express how the engineering formulas that we use in a design work with one another to figure out what the constraints and the design parameters of the system are. Now, many people have talked about systems modeling language being so complex, I can't use the language. Well, you've got to combine the language with some sort of methodology in order for it to be useful. Otherwise, you'll end up bouncing around the language and never really bouncing around doing various systems modeling language diagrams and never really having a connectivity between the various diagrams and the various design information. The commercially available systems modeling language tools are very good at expressing the language and are fully compliant with all of the little nuances and idiosyncrasies, if you will, of the standard that is systems modeling language. Because there is relationship between elements in our architecture in the model-based system engineering tool set, it doesn't really compare at all to PowerPoint or Visio slides. Each of the PowerPoint or Visio diagrams that you create are independent standalone diagrams. And there's no notion of the connectivity from one diagram to another diagram. How do I trace from the fact that this particular block has a part property to and show me the connections between those part properties? You can't express that in PowerPoint or Visio. They're just pictures. They're not really representative of the underlying model. In systems modeling language, we can show how systems behave and are connected differently in different contexts or usages or situations of a particular system. We can show how we can make a particular design or we can take a system and configure it in particular ways at different points in time. We can simulate our systems model because OMG is compatible with the functional mockup language. There we can show how a system operates and we can show how a system is simulated. And we can take the modeling language, and the modeling language has allowances for how to extend the language to make it adaptable and configurable based upon your particular industry or your particular organizational needs. So those are all of the reasons why I want to use systems modeling language. It may appear complex, but frankly, because of the complexity of the systems we're dealing with today, we've got to have a tool set, we've got to have a framework, we've got to have a language that allows us to extend it, to use it with certain rules so that we can express the complexity of our designs. So we've talked about why MBSE, we've talked about the systems modeling language. And so now we're going to talk about something, a diagram that I've shown you already, which is the MagicGrid. And we're going to walk through how I take MagicGrid and how I break that down. And we're going to jump into a model and see how the things I'm showing in the MagicGrid are actual artifacts from a system design model. So we saw this diagram earlier. This is the overall MagicGrid concept here. And so again, this is ISO 15288 model, and we look at the problem, the solution, and the implementation. This MagicGrid model, as it's shown here, is also available from us vis-a-vis a book called the MagicGrid Book of Knowledge. And so what I've done here in this chart is taken that problem, solution, and implementation and broken it down a little more. So what I'm going to look at here is the problem statement. What is the problem? What are we trying to achieve? What are the stakeholder needs that we have to start out? And how do we take those stakeholder needs and then advance through understanding those stakeholder needs and breaking them down, if you will, pulling them apart and understanding how we do some set of design and how we end up getting from stakeholder needs through documentation development, if you will, of systems requirements. And we're going to do that to handle what we call a systems requirement review. So in that systems requirement review, we want to take stakeholder needs, do the analysis that's represented in these fields over here, and then end up with getting to some system level understanding. From the system level understanding then through that SRR, understanding the actual systems requirements, and we're showing traceability of how we get to those systems requirements from the initial stakeholder needs. Then we'll build our model further and look at how do we understand the system behavior? How do we break that system into subsystem and some components? And eventually I'm going to work my way down into what's called a preliminary design review. And then from there, I'm going to get into this actual implementation and the things that we keep in the model-based systems engineering world in CAMIO Systems Modeler that show the actual physical system. And that would be accomplished once we get all this done through what we call a critical design review. So taking this one step further, I'm going to break this concept into 3 layers here. And I'm going to talk about how we solve the first layer. Then we're going to look into how do we do the solution architecture and what we call a logical architecture through the preliminary design review. And then we're going to talk about how we get to the physical architecture and accomplish the critical design review. So to begin with, we want to get to something called an SRR. Well, how do we do that? We start with some stakeholder needs here, and we develop those, we review those stakeholder needs, and we start talking about, well, what do we understand as, when I read those requirements, what do I understand as the system that we would need to solve those requirements? So I develop things like a use case diagram, an activity diagram, block definition diagram. I can further that with understanding some measures of effectiveness that I need in the overall system. Generally, the stakeholder has some high-level performance factors they need. And once I do that, I can break this down into some logical subsystem. And eventually, from all of this, as I start doing my work, I can show traceability from the system context back through the use cases, back to these, to the stakeholder needs, excuse me. And eventually then I can get through all of this understanding, I can get to the systems requirements, a system requirement table, and a derived matrix that shows me the traceability between the systems requirements and the actual stakeholder needs. Well, that's all fine, but how do I actually do that in the model? So I'm gonna come out of my presentation here and let's talk a little bit about CAMIO Systems Modeler and how CAMIO Systems Modeler works in this using model-based systems engineering in the systems modeling language. So this is the graphical user interface. This is the screen you use when we actually do system design here in CAMIO Systems Modeler. And the big thing to look at here is this containment tree. There's a containment tree over here on the upper left-hand side, and this shows us our model. Now, this particular design model also has some grayed out things in here. And these grayed out things are actually projects that I'm using to facilitate my design. So I have things in my company here, before I go too much further, the concept here is this water distribution system that I want to create, that I want to do design for. And my customers come to me and said, hey, I need to pump water from a supply reservoir up into a water distribution tower, And then I'm going to use that water to use gravity feed to supply some residents of an undeveloped area of the world, to supply them with fresh water that they can use for sanitary purposes in their homes. So I have this generic sort of understanding here of what I want to do. And so although this is not really a life science, a pure life science project here, it has all the hallmarks of any system that we would want to design for any application. In that I have some beginning requirements and I have some beginning analysis, but I got to get into the details of how big does a pump need to be? How much pipe do I need to have? How am I going to control water in this tower? Are there certain shutoffs or safeties that I need to have in the tower? I have a supply reservoir here, but are there safeties I need to, if I get to some low level in the supply reservoir, for example, would I need to turn the system off? How do I control the flow? All those questions come out when you look at any sort of system design. And so over here, I have this containment tree, and I'm going to start here with a conceptual model. So this is the conceptual model of my design. And this is where I'm going to focus for my first level. That problem area is all handled up here in this conceptual model. And eventually then, once I do some analysis here, I'll be able to get into this logical model. So what did I talk about? So this is my conceptual diagram here. If I want to get through the SRR, there are certain things I need to do. So although there are a number of elements over here, and you can see various elements here. Here's the use cases down here and how the containment tree does the use cases and how we do that. Here's some structure of the system. And I'm just looking at the structure, some top level elements and those sorts of things. And they're all contained over here in the containment tree. And the containment tree shows me the relationship between things, but I'm just going to walk through the diagram. So here, to begin with, I had some user requirements, and I can express those requirements by this diagram. So here is a typical systems modeling language diagram with several sets of requirements, and I have some rationale associated with them. I can also express that in a table here, which gives me the name of the requirement and any rationale that I have on it. And if I needed to here, I can modify this table, and I can show the text of the requirement. And so when I do that now, it added the text in the document, in the table here. But now I see the name of the requirement, what the text is from the user, and what rationale I have provided for this for these requirements. So use cases. I said I was going to create some use cases. So the use cases are here in the model, and if I look at my use case diagram here, I can see the use cases that I have in the model. But if I go back in here, I can show from this diagram, I created these use cases. These use cases have some relationship to the requirements that I have. So here's my user requirements, and I'm showing that these use cases are used to satisfy these requirements. And I use the relationship called refine to do that. And I can see that all of my use cases have at least one refined requirement to it, and all my requirements are represented in at least one of the use cases. So I'm doing some model checking as I'm going along to do this. And then I can show user requirements, and I can go back to my user requirements here, and in a different table show which use cases refine these individual requirements. So this is helping me understand the system in conjunction with my audience. I can also look at use cases in a report, and I'm just double clicking this, and I'm going to go over here to a use case report. So here's the use case report for this system. Actually, the last time I ran this report was in July when I did a similar webinar. When you get down into here, and this is an actual report that takes model information out of the model. If we go down here, you see the actual use case diagram, and the rest of this Word document pulls information out of the model to show me all the information on these individual use cases. So what's my structure? After I've read those requirements, I have some use cases. Now I can look at the actual structure of the diagram. So here, this is showing me the structure of the system that I want to design. And now, so I understand all that. And so now I can make a systems requirement table where these are the requirements I'm going to design my system to. So these would be system level requirements, if you will. So these are my system level requirements. And from there, I also understand how am I tracing from those top level requirements you gave me, stakeholders. Here are the actual systems requirements that I want to do my design model to. So I can pull this over here so you can see them all, but I can create those or see those, how we have that traceability. So this is all part of this conceptual model. So going back to my presentation here, I have gone through this analysis to get to here, right? So the next thing I want to do is go down to work down to getting a preliminary design review. So this design review now requires us to build out the system structure, understand the subsystems, get the behavior and those sorts of things now. So again, I work across these rows. I have requirements. I can understand reading the requirements. I understand what systems behavior I need, what sort of system structure do I need, what sort of system parameters do I need. These things have traceability. And from this system level, then I can also look at the subsystem level. What subsystems do I have? When I make the system structure up here, I get to a subsystem structure. I look at the behavior I need to have, allocate that onto a subsystem structure, understand what parameters I need for that subsystem, for the individual subsystems. And I understand now that I have these subsystems with requirements, and I have to trace from these individual subsystem requirements back up to the system requirements, so I can do all that and eventually get down to some individual components that I think I want to design and what the requirements are for those components. So again, I can express all of this in my model, and I'm going to come out of this PowerPoint slide here for a second, and I'm going to go back into my design model. And we'll look at here now at what the logical model tells us. What is the design of the system? What requirements do I have? What structure, what activities, what parametric analysis am I going to do? What sort of libraries do I have for interfaces? What interfaces have I defined? What signals, what value types do I have? And ultimately I get to a PDR package to bring all these things together. So I'm going to open up this PDR package here. Let me close up this drawing. So now in this preliminary design review, I have the requirements here. I have some structural design at the context level. Then I have some structural design details, some behavior that I want to look at. And finally, I have some parametric analysis that tells me what's going to happen. And then all the way down here, I have my component specs for what are the individual components I need to procure or produce in order to make this design. So let's start up here. We have a systems requirement table. So these are the systems requirements, right? This is the systems requirements that I started with at the very beginning. From those requirements, I could look at, I'll come back to the satisfy matrix here in a minute to look at the system elements that are there. But now I would start to look at what are the, what sort of activities do I have? So here is, may have produced, for instance, this little this little activity diagram that shows me which components of my architecture are doing which functions and how does it do that. And just very briefly here, I'm just going to run this really quick, but these activity diagrams, state machine diagrams, things can be simulated. I'm just going to run through a quick simulation here of this, just so you can see how we do this. But we basically walk our way through the design, and the simulator will check on how we do things. It's going to ask me, oh, did you want me to turn on the pump? Is the water level below maximum? So if the water level is less than maximum, yes, I'm going to turn on the pump here. It's going to continue to work to detect water. Is it greater than maximum? I'm going to say no here, and I'll say no for this one. This will allow me to continue to go over here. Now let me get to a water level. I'll say yes here, and I'm going to say no here, and this will give me what we call a low supply shutoff. In a minute, is water level less than minimum? We say yes. This will give me a low supply shutoff, which is telling me that the system detected a low reservoir level, and that is what caused my system to stop. So there's more to this diagram, but I just want to get back into my systems model. So that's the type of behavior analysis I can do. I can also do state machine diagrams. So this is the system classifier behavior for the tank. There's another simulation that goes on here, but basically it tells me the state-based behavior of the system. And all these, the state-based and activity diagrams, those all end up going into your safety analysis and things like that in your system design. I can show activities, and I end up having a number of activities. Shall we close this? I have a number of activities here, and those get related to what are the blocks in my system. So I take my activities, I allocate them to a physical architecture. I can see over here the system. This is the system context, DDD, and then I got more detail here in the logical structure. So this is the WDS system has a monitor control, and I have all these individual system level elements and sensors and certain things that are there because of reading the analysis or reading the requirements that I had. Then I also have the notion of interface diagrams here. So this is the system controller and what interfaces it has to have with which either internal or external things. I can look at also the this is how the water is flowing through the system from the reservoir to the pump system, from the pump into the discharge piping system and up into the storage tank. So those diagrams all express certain things I learned from doing the analysis from the systems, from the requirements to the functions to the system level. I can also look at then, how big of a pump do I need to have? How does that pump work? So I have a notion of what the water distribution system needs, and I compare that to the actual total pump power analysis, which is a used model, and I can then do some analytics there. But eventually I can then also get into an analysis here that tells me things like, if the discharge level is only 62 meters, then I need a pump that has 168 horsepower in it. But if I have to go to like 100 meters in discharge height, through that parametric analysis, I can simulate that again, and it shows me that now I have to have a 251 horsepower pump. So the discharge height, as well as I could do another analysis to say, if I have to pump further, how is that going to affect my system? So now I can look at trade-offs, or I can look at when I survey the actual site, if I have 250 feet, then I only need a pump of this length, or if I survey the site, I realize that tower is really it's really 100 meters away from the pumping station, then I may have to get a different pump. So that allows me to do the trade-off analysis within the model. And eventually then I can get down to understanding individual procurement specifications. So on the pipe system, I'm going to have pipe with certain qualities in it. How many do I need? What's the roughness factor? What's the diameter of the pipe? Things like that. This gives me the total pump power analysis. This is another diagram. This is showing me the actual equations and how they relate to one another and how I get input equations to put in there. It's all part of my simulation engine in the system design. And so I wanted to go back up here because I have system elements and then I have subsystem elements. So now I can look at, well, here are all the systems requirements that I had. How do those requirements relate to the functions, which are in this part of the model here, and the components that I picked for the system, and I can show that relationship between those two. So I have what's called a satisfied relationship to trace through those. Now, what's interesting about that is if I if I was to say something like, I want to switch out the flow sensor. Well, if I'm going to switch out the flow sensor, here is the requirement that the flow sensor meets. And though I don't have it on this table, I can track from this flow sensor to the requirement and actually to the test case that I did to test that requirement or to test that flow sensor. So when the model is built out, when I go to buy flow sensors, I know what requirement those flow sensors have to meet and what test cases I need for those flow sensors. Going back into my slides here for a second. So I've shown you how to build through all of these things to show the satisfy, derive, and allocate requirements here. The next thing is once I go from a PDR, then I need to get to the detailed design review, critical design review. And to do that, I'm going to do a little more investigation here, but then there will also be a number of SME equivalent things, an electrical layout diagram, electronics diagram, a pipe layout diagram. So that would be done through 2D and 3D models, which are not part of Cameo Systems Modeler, but are done in the platform. And they can also be simulated in the platform to show us how the selection of individual components meets individual individual requirements and parameters for the individual system. So if I go back into my model here, I end up with a physical model and I end up with individual requirements here for individual systems. And I can look at things like the derived matrix to show me what fittings are needed or how the flow rate requirements get broken down into individual requirements on components here. And this will show me things like the parts tree. So I need a certain number of parts. Here are all the parts I need. And I can show in the model, I need different sections of piping with I need 1 meter section piping. I need 6 of those. I need 10, 20 meter pipings. Here are all the fittings that I need for the design. Here are all the sensors I have to have for the design. Here's the harness cable and what needs to go into it. But again, those are all represented again in a package environment here. I can bring all those onto one diagram and be able to navigate back and forth to see, okay, if I'm in a critical design, here is the pipe system. Here are all the things I need in the pipe system. And then here's the number of length of different kinds of pipe that I need. And this table is derived from this diagram and the information on this diagram. And if I was to change this, let me change the multiplicity here. I change this to be 7, for example, and I look at this in another view. When I look at this, if I did this, these are the requirements here. There was a table here, pipe length table. So this just showed me the pipe length. But if I go back here to this design and I take this, I'm going to change this 10 meter section to be 15. And this is the power of model-based system engineering. I changed the number of things here. If I go back to this table, you'll see that 2 meter section has been changed to 15 from what it was earlier. And I can look at all the individual components as to what I need for the individual components and how those are done. And when I get down now into like this understanding here, here's the power relay assembly, the circuit board, and the UI panel. Well, those things now, I have those defined here. I can tell you requirements for those. And then the actual implemented design there would be done in the other, this design would be connected to and completed by other software that we have in the platform. And this design would continue to be connected to one another. So I'm going to go back to my PowerPoint slide here just to conclude. Back to that. So we have, what I've tried to show you here is the fact that I've taken some initial stakeholder needs here, and just through the 10 or 12 requirements that I had here as stakeholder needs, I went through this design process using the systems modeling language in the model-based system engineering toolkit, or model-based system engineering tool set called Cameo Systems Modeler, and I went through and made a very descriptive, detailed design, which would then be backed up by other things in our platform. Cameo Systems Modeler is right here. It's the system design tool set. We also have a software design toolkit called MagicDraw, which uses UML. And we have Cameo Enterprise Architect, which does more of the enterprise architecture things. And I also used in this Cameo Simulation Toolkit to show how I simulated things. And the rest of the platform, you'll get some understanding of that when we go to the next couple of lectures. So I'm going to turn it back over. Do we have any questions on this?
Hi, Ron. Thank you so much. That was an excellent presentation. We'll go ahead and move into the Q&A sessions for today. And we have had a few come in already, actually. So let's go ahead and get started. The first question is, in the medical device development industry, we need to conduct safety analyses. How is this accomplished in an MBSE environment?
Well, there's a couple of things you can do. One is, I'm going to go back to close up some of my diagrams here. I'm going to go back to one of those diagrams from the PDR, but I can look at things like an activity diagram, and I can see on the activity diagram, what things how would losing a signal, for example, affect the system, and I can actually take the signal out of here and see how the system would change. But there is also an add-on to this modeling environment called the Safety and Reliability Analysis Toolset. And that toolset allows me to do failure modes, effects, and criticality analysis. So I know that there's a standard out there in the medical device industry that talks about engineering for safety and human interaction. And that add-on goes through, and you can do the analysis in the tool set, and then you can connect individual things like this detect water level in tank, for example. This activity can be connected to a safety feature, and you can do the analysis in there to understand what would be the impact of losing that signal. So really, mostly through the safety and reliability analysis plugin.
Perfect, thank you. The next question that's come in, how does SysML compare to or contrast with TOGAF?
Okay, so TOGAF, let me go back to this. I want to go back to this, so TOGAF is an enterprise architecture framework. So in TOGAF, we look at the things a business wants to do, how they want to do it, what capabilities they want to bring into it, and what operational activities and performer nodes are part of it. And that is done using Cameo Enterprise Architecture. To build Cameo Enterprise Architecture, we take Cameo Systems Modeler and we put several enterprise architecture frameworks on top of that. And we basically extend the systems modeling language to be able to meet the needs of the unified architecture framework, the unified profile for DODAF and MODAF, and TOGAF and Zachman framework and those other frameworks. So Cameo Systems Modeler does the solution side or the resources side of understanding the operations and performers and activities. And if someone's interested in that, they can contact us, and I can give you a brief demonstration on how we handle enterprise architecture using Cameo Enterprise Architect.
Great. The next question we have, we work in a distributed team in my company. How do we share models, and are we able to work collectively on one instance of the system design model?
Yeah, that's a great question, because what I've really shown you here is a model that I have on my machine, so to speak. It's only me on my computer looking at the model. But we have the ability, we have another product that goes hand in hand with Cameo Systems Modeler, and that's called Teamwork Cloud. And so you see this little collaboration area right here. So I can actually log in to a Teamwork Cloud instance. And when I log into Teamwork Cloud, I can take a project off of Teamwork Cloud, and I can start start using that project. So I'm just going to show you here. I can log into my Teamwork Cloud here, our company Teamwork Cloud. And when I get in there, you'll see a number of different models. Maybe I can pull one up here real quick. So now that I'm in there, I can look at all the projects that are on Teamwork Cloud. And so we actually on the systems engineering team, we're sharing all these models. So when I look at, let me find the systems modeling language 5-day intensive class, here's this actual model that I have here. But I can actually pull the model in, and when I do that, I can then lock elements and make changes to it, and 2 or 3 of us can be working in the model all at the same time. We just have to work in different areas. We can't change the same element at the same time, but if I was doing functional analysis as opposed to requirement analysis with somebody else, we could be in the model at the same time, and the model is updated in real time as we add our changes to it. And there's lots of abilities here to basically do role-based access. So I could be a reader, I could be a reviewer, I could be a manager, those sorts of things. So there's a whole collaborative aspect to being able to do this model-based systems engineering.
Excellent. The next question, is there a connector to Simulink?
Yes, there is. So Simulink is a MATLAB product, right? And so our simulator, our simulation toolkit can connect to Simulink, and I can basically, I don't have a demonstration here, and I actually wouldn't work because I don't have a Simulink license on my desktop computer. But I basically can take let me find a particular model here that you guys would probably resonate with. I can take let me go to this analysis package in here. I can take a parametric analysis package like this pump power analysis here, and actually here is the actual parametric diagram. So I can take and connect this to a set of equations in Simulink, and you'll actually get a block that shows up here, and I can make my connections here to Simulink and have Simulink run the simulation, then push the values back into the Cameo systems model.
Perfect. The next question, how do we get information out of the MBSE model into a format that I can use to review with my customer?
So there's a couple of very basic, simple ways we can do that. One way, and one thing that a lot of people do is, I'll go up here to my SRR package. I can look at any one of these tables. Let me grab a table here. This is a table with rationale, and I add rationale in here. So I have the ability to synchronize this with Excel files. So I can take this table, put it in an Excel format. I can edit it in Excel, and then I can push changes back into my model. The other way to do this, the other capacity here is, of course, I can also take out any individual diagram and put it on a PowerPoint chart for someone to look at. There's a feature called Cameo Collaborator, which basically publishes the model to a website so people can look at it and they can make comments to it. They don't have to have a license. They just see you publish it to a website. You can look at a diagram or a table, and they can make a comment on it, and you can bring those comments back into the model and then adjudicate them. And then the last thing is we have the ability to do the report wizard here. We have a whole series of reports that are here. I showed you one very quickly in the beginning, which was the use case report, but there's a number of other reports that can come out of this, allocation tables. We have ICD tables, things like that. There's a whole reporting feature part of this, and it basically takes the information in the model, pulls it out, and puts it in a document format that you can read. And it's based on, the thing is, it's based upon the information in the model. So you can't edit it in a Word document, but you can see where your errors are and then go back into the model and make changes. So it's really 3 ways: basic Excel import, export, using the report wizard, or just exporting and creating, looking at the views in the system.
Perfect. And I think we have time for one more question. Does the document generation feature allow you to generate an interface control document, or ICD?
Yes, it does. You can have an interface control document, and let me find a quick little ICD that I can pull out here. Let me go in, let me close this. But what we have in here is what we call white box and black box ICD tables. So I'm going to look here at, I don't want this, I want my structure here. I'm going to look at, so I'm going to take the monitor and control subsystem, and I'm going to create a diagram here. This is how you actually create diagrams. And instead of this, what I want to do is I want to do a, I'll do a black box ICD table. And what this is going to do is sample type. I have to do a white box ICD because this is, I don't have details inside here, but what I can do is do the white box ICD table here because I don't have design inside of there. So this is showing me all of the parts and ports that are here, what items flow across them, and what is on the other end of the interface. So each one of these is indicating an interface. So here is the port that interface is on, and a port has a specific meaning in the systems modeling language, but it just tells me what it exposes for people to look at. So here is this flow rate sensor has this port. This is a feature of the port. I don't have an item to find on here. This is the other end of that connector is in this port, which has this feature, which is on this part. And so that ICD table, that document is really pulling apart this entire ICD table, if you will, and giving me all the information on there. The other unique thing about this is you can run these reports at any time, and I can look at this by inspection and say, how come I don't have an item flow identified here? And I might want to do some investigation to find out why didn't I identify an item to flow across this particular connector. And it might be because I'm not to that point in the architecture. It might be an error that I had in the model at this point that I just need to correct.
Perfect. Great. Well, that is all the questions we have time for. Thank you again, Ron, for sharing your time and expertise today. It's clear that the audience found this information very useful and informative. Thanks everybody for joining, and we hope to see you at the next one. Have a good day.
All right, thank you.